All right, so today we're going to look at writing exponential models and what goes into actually taking real-life information and putting it into a model. So to do that, we have this general form of an exponential. F of t equals v sub 0 times 1 plus r to the power of t. Looks all complicated, but it's not really that complicated. F of t is simply our function, the thing we're trying to get the value of. Sometimes this is our target value. V sub 0, well, that is our initial value. The little sub 0 is saying when time is 0. So initial value, the value at the very beginning. What is it when t is equal to 0? Why does that work? Because if t is 0, then this whole thing to the power of 0 is just 1. R is our rate of change, and t is our amount of time. And it's important as we do these to think about, is t years, is it months, is it days, what is it exactly that it represents? Sometimes we're given r, a rate of change. Other times we're not given a rate of change, we're given a change factor. So sometimes we use r, our rate of change, and other times we use 1 plus r, our change factor, to write these models. So it's important that you recognize, is the information it's telling me, is this a rate of change or is it a factor of change? And being able to differentiate between those two is very important. So let's look at some examples of these things. So write a model to represent this situation. Population of ants is measured to have 50 ants. Over the next 12 days, the population increases 3% each day. So first of all, fix my grammar, that should be increases, not increase. So we have a population of ants. So I'm going to say P is ant population, T is day number. So right away I represent, what do we have? So my equation is going to be P equals v sub 0 times 1 plus r to the power of t. Well, v sub 0, that's the initial value. The initial value was 50. So we get p equals 50 times, what do we have? We have an increase of 3% each day. So that's a rate of change. So it is 1 plus 0.03 to the power of t. And we can simplify that, and so we can say our population of ants is 50 times 1.03 to the power of t. And you might ask, well, what's up with that 12? Well, the 12 simply just says, hey, this equation really is only valid for t up to 12. It doesn't make sense if we do a t of 30 or 40 or 50. And sometimes when you're looking at problems, it's going to give you that information that says how long is this model valid. So we'd say t is a day number. We could say that 0 is less than or equal to t, it's less than or equal to 12 is our domain. Most of the other questions don't have that limitation on them. But it's always, when you're dealing with these situations, it's always important to think about those possibilities. So here's our model. P equals 50 times 1.03 to the power of t. So if I wanted to know how much is the population on day 10, I can plug 10 in for t and figure out that value. Let's look at these next problems. And I want you to start with this one and see how well you can do at writing this model. And in just a moment, I will write it. But first, I'm going to let you pause the video. And since you've now paused it, you've come back, means you've already got your model written. So let's start with our variables. I'm going to have C is car value, T is months since purchase. And so we write our equation. We have C equals V sub 0, 1 plus R to the T. Well, in this case, C equals the initial value, 93,000, times 1 plus R. Well, in this case, it loses loses value at 10% per month. So R is going to be negative 0.10, or just 0.1 to the power of t. And so our model becomes C equals 93,000 times 0.9 to the power of t. And there's our model. Just to add on to that, how much is this car worth after 3 years? Well, if we want to do that, we're going to have to go in and we're going to see, well, t is months. So if it's 3 years, we want t to equal 36 months. So then we're going to do C equals 93,000 times 0.9 to the power of 36. So we pull up our trusty calculator, and we should do 93,000 times 0.9 to the power of 36. And the car is worth giving you a chance to calculate this, $2,095.14 after 3 years. Don't think that 10% per month is valid, though I think the first couple of days it probably does that, but then it slows down later on. So I don't think a $93,000 car is only worth $2,000 after 3 years. But that's what the model says. But it's always important when you see a model, is this reasonable? Because what's the good of a model if it doesn't really hit real life? In this case, I made up some numbers. Sorry. But as we look at some models, it's important to see if our answer makes sense. There are 3 more problems here. Population in Singapore with a growth rate, plate of cookies, and a population of rabbits. All of these kind of bizarre. Let's look at the plate of cookies, which is an interesting problem that has no bearing on real life. Got a plate of cookies, has 40 cookies on day 4, it has 30 cookies on day 3, or day 5. Now obviously you could look at this and say, well, hey, it looks like we are subtracting 10 each day, so day 6 will be 20, day 7 will be 10, day 8 will be 0. Except the instructions at the top say to write an exponential model. So we've got to assume that there's an exponential model going on here. So what does that mean? What are we multiplying by each day? Well, we need to get from 40 on one day to 30 on the next day. Let's play around with this model and see what happens. So let's do C equals number of cookies, and T is day number. Now we can do this a couple of different ways. We can do day number. We could also say day number since day 4. And having day number since day 4 makes it a little bit easier to work with. Let's say days since day 4, just to make our life a little bit easier, which means that it is 40 when t equals 0, and it is 30 when t equals 1. Okay, so let's write our model. We know that C equals V sub 0 of 1 plus R to the t. Well, V sub 0 is the value when t is 0, which we set t equals 0 to be day 4, 40 days. So C equals 40 times something to the power of t. Day 1 is 30. When t is 1, we get 30. So I need to multiply by something so that we can have 30 equals 40 times something to the power of 1. What is that something? Well, I'll put an x here. Well, I'm just going to leave it as 1 plus r. So then the 1 doesn't matter. We divide and we get 3/4 is 1 plus r. We could solve and get r, but there's no need. let's plug this back in. 1 plus r is 3/4. And so there is our model. C equals 40 times 3/4 to the power of t. Now, what values of t make sense? In this case, well, day 4, probably we could go back to day 1 or maybe day 0. So t is day since 4, and maybe we would say negative 4 is less than t is less than who knows what. I'd like you to answer 2 questions off of this. How many on day 0, when will there be less than 1 cookie left? So that one, assume, eventually we're going to do this and you're going to end up with fractions of cookies on days. Even day 6 is going to have a fractional cookie. Eventually it'll break down how many days until there's 1 cookie left. This is going to require you using the POW and the log function and solving this equation to work it out. Day 0, well, day 4 is t equals 0, so day 0 would be t equals negative 4. So you just put in negative 4 and you can work that one out. Hopefully that's good enough. Notice here we did the 1 plus r. Actually, I will look at a little bit of the next question. I just want to mention this just a little bit here. Not going to do the whole problem, but remember what I talked about. Sometimes a problem gives you a growth factor instead of a rate. In this case, the growth factor is 150%. So 1 plus r equals 150%. Or 1 plus r equals 1.5. So our equation is going to be 1.5 to the power of t. It will not be 2.5. 1 plus r is 1.5 because the growth factor is 150%. It's not a growth rate. There's a big difference between a growth factor and a growth rate. All right, so hopefully you can complete these up and make sure you answer the questions.